Thanks. Yeah, I'm very happy to be here, and thanks a lot for the invitation and the opportunity to talk about my favorite topic, higher dimensional isogenies, and all of this in the context of isogeny-based cryptography. Well, isogeny-based cryptography is one of the proposals for post-quantum cryptography, and well, it has a the recent history has been quite turbulent, and lots of this has to do with our increasing understanding of higher dimensional isogenies. And if we look at dimensions in general that were used in isogeny-based cryptography from the start, and most of the research actually focused on the isogenies in dimension 1. And it was only a few years ago that people also got interested in the two-dimensional setting. But at least in the beginning, this research was considered a bit more esoterical and maybe only interesting to the more mathematical people in the community. However, then, as I mentioned, there were some turbulences, and one very important thing that was figured out was that there is actually an important connection between the dimension 1 isogenies and dimension 2 isogenies. And starting from this event, suddenly in the last 2 years, there appeared many new isogeny-based cryptographic protocols that make use of many different dimensions. And my talk will essentially follow these 4 different chapters. So I'll start by talking a bit about dimension 1 isogeny-based crypto to set the setting. Yeah. So what's the one-dimensional picture? In dimension 1, the main object that we are studying are elliptic curves. I guess elliptic curves are well known to everybody here, and the reason for that is that there is a group structure defined on these elliptic curves. So there's also this nice geometrical description that we can add 2 points on an elliptic curve by just drawing a line through these 2 points. We get a third intersection point, which we reflect along the x-axis, and we get the sum of the 2 points. If we can sum 2 points, what we can also do is by iteratively doing this to multiply a point by an integer. And what this gives us is, in a well-defined setting, a cryptographic one-way function. Because so by using some double and add strategies, we can do this multiplication quite fast. And on the other hand, it's believed to be hard to invert this multiplication by an integer. However, the reason that we're here is that this is not a post-quantum secure one-way function. And that's also why in isogeny-based cryptography, we not only consider elliptic curves, but what we consider are isogenies of elliptic curves. Such isogenies, you can just think of them as a map between, or I mean, they are a map between 2 elliptic curves with some special properties. In particular, something that we want, I mean, we have this group structure on elliptic curves, and these maps have to preserve the group structure. So in particular, they are group homomorphisms. In the talk, I will often talk about N isogenies or L isogenies. And what this means is, so, I mean, we have a group homomorphism. This means this has a kernel. And indeed, isogenies always have a finite kernel. And now an N isogeny is just an isogeny with a cyclic kernel of order N. In general, we can compute such an isogeny using formulas by Velou that are also well known for quite some time. And this can be done in time O of N. There's also a faster algorithm that can be used, which is particularly good if we have large values of N, which works in square root of N time. However, so our goal will be to create a one-way function with such isogenies. And in the end, we would like to compute isogenies of exponential degree. If we use, so the degree is also this integer N here. So if we use just a standard Velou formula to do this, this will take exponential time. So that's not really what we want. And the standard solution for this is to use N values for N that are highly composite numbers. And here I sketched what we would do in a case if, for instance, N is equal to 2 to the k, so some power of 2. And then the idea is just to decompose the entire isogeny computations into smaller isogeny computations with small degree. And so we can compute this isogeny in time logarithmic in N. And a common way to think about those smooth degree isogenies is to look at so-called isogeny graphs. When I say isogeny graph, I really mean a graph in a graph theoretical sense. So we have vertices and edges. In this case, the vertices represent elliptic curves, and the edges represent isogenies between these elliptic curves. And depending on the setup that we wish to have, we fix some small prime number, or don't need to be prime numbers, but usually we fix some small primes, L1 up to Ln, for which we can compute isogenies efficiently because, yeah, they are small. And and here in those two graphs, the different colors represent the different Li individually. And so what this means is we can walk efficiently in the graph. And by taking a walk of polynomial length, we obtain an isogeny of exponential degree that's efficiently computable. And maybe from this description, you already see how this one-way function will look like that we obtain from this. And that's essentially, so what we do is we fix a graph that we want to compute in the beginning, and we fix some starting curve, so a vertex in this graph. And then on input, some bit string. This will define a path in the graph. This path will only be used internally, and the output of the one-way function will be the end vertex of the graph. And why is this a one-way function? So, computing this path is something that we can do fast. However, it's believed to be hard if only given the starting vertex and the end vertex to really find this path between the elliptic curves. Of course, the hardness of the problem also depends on the isogeny graph that we chose, but there are some different instances for which we believe that this is a hard problem. And in particular, there are also no efficient quantum algorithms known that can solve this problem. And that's what makes isogenies a proposal for post-quantum cryptography. Something that's particularly nice about this one-way function is that, similar to the group-based setting, we can, under certain circumstances, also define the Diffie-Hellman key exchange protocol. And in a simplified way, I sketched how this works here. So again, we fix some isogeny graph in which we want to work and a starting vertex. Now we have two parties, Alice and Bob. And what they do, so we start with Alice. She just chooses a secret path in the isogeny graph. Bob will do the same thing. He chooses another secret path in the graph. And now they both only exchange the end vertices of their graphs. And then finally, they repeat the path starting at each other's end vertex. Repeating the path is actually the crucial point here. And it's absolutely non-obvious how to repeat a path in a good way. Because, I mean, if you start at a different vertex, it might not be clear what it means to repeat this path. And there are different solutions to this problem that result in making these paths actually commute so that they both end up in the same end vertex, which can then be their shared secret key. And yeah, so to finish this prior on the one-dimensional setting, I summarized some of the most important proposals for cryptographic primitives that happened in the one-dimensional setting. This all started with a proposal by Cobain already in 1997, who suggested to use group actions that are based on isogenies in cryptography. However, this hasn't been published, and a similar idea was rediscovered independently by Rostovtsev and Stolbanov. This group action-based schemes, they all work with this nicely looking graph that we already saw 2 slides ago. So it's the one on the right-hand side. And this has to do with the fact that we have a commutative group action sitting behind this. These first 2 proposals weren't very efficient, and the first efficient instantiation of such a group action was only obtained in 2018 by the introduction of Seaside. This uses a different set of vertices. However, the graph will still have similar properties. And in this nicely looking graph, and which is common to all the protocols on the right-hand side, it's easy to say how to repeat paths in such a way that they commute. So there, somehow we have a more natural definition of a Diffie-Hellman protocol. It's a bit different if we go to the other side, where we have this kind of chaotic looking isogeny graph. Here, the first proposal to use such a type of graph was in 2009. And here the idea was to construct a cryptographic hash function. So this is maybe the easiest constructions that you can have if you have a one-way function. And later, or 2 years later, DeFeo and Yao also had the idea how to actually obtain a Diffie-Hellman protocol on this chaotically looking graph. And this required the additional sending of some more information, which are torsion points. And then finally, also to mention this, there's also the SkiSign protocol, which is one of the candidates submitted to the NIST competition for signatures. This also works on this side of the protocols. Okay, that's all I wanted to say about the one-dimensional setting for now. And now let's turn to the two-dimensional picture. So maybe the first question that you might ask yourself is, okay, what's an elliptic curve of dimension 2? To answer this question and also maybe phrase it in a bit more precise way, we have to, so what do we understand formally by an elliptic curve? To say this in more mathematical terms, an elliptic curve is a variety. This just means it's defined by some equation. So here, like the equation y squared equals x cubed plus ax plus b. And as such, a variety, it has dimension 1. And in general, that's true for any curve. I mean, it's what you would expect from a definition of dimension. If you have a curve, that's some object of dimension 1. And what makes elliptic curves special among the set of all curves is that we have this group structure defined on an elliptic curve. And the formal way to say what an elliptic curve is that it is a principally polarized abelian variety of dimension 1. And so the question on my slide should have actually been, what's a principally polarized abelian variety of dimension 2? Okay, so now we want to somehow construct an analog in dimension 2. And the easiest way to do this is obtained by the observation that 1 plus 1 is 2. And that's what we do is we just take a product of two elliptic curves. If you have, I mean, it's similar as in Euclidean geometry. If you have two lines, you take a product of them, you get a plane, which is something of dimension 2. And in the same way, we can just take a product of two elliptic curves. This also preserves the group structure that we have on it, and we get something of dimension 2. However, this is not the standard or the most generic object that we have in dimension 2. And to describe the more generic object, we need to also talk about genus 2 curves. A genus 2 curve is a hyperelliptic curve, so that's something that's defined of an equation of the form y squared equals f of x. That's similar to an elliptic curve, only that here the polynomial f has degree 5 or 6. And well, I said that all curves have dimension 1, so that's not yet what we want to have. And also elliptic curves are the only curves that have this group structure on them. So we also don't have a group structure on genus 2 curves. Instead, what we look at are so-called Jacobian of genus 2 curves. I don't have time to give a formal definition of this, and maybe you also don't want to see it. But maybe, so some things that how one can think about it is, I mean, it's a surface, so something of dimension 2. And the description as a variety is quite complicated. So for an elliptic curve, we could just define it as a variety by giving one equation. If we would want to do the same thing here for this Jacobian, which has dimension 2, one way to do this is to look at a 15-dimensional space and 72 equations defined in this 15-dimensional space, which then cuts out the variety. So obviously, that's not a description that's somehow suitable for cryptography or for efficient computations. And an easier way to think about these surfaces is just to think about them as consisting of pairs of points of the hyperelliptic curve. And maybe you can also imagine the group law in a similar way as for elliptic curves, where now you want to add two pairs of points to get a third pair of points. And for elliptic curves, we've drawn this line through the ellipse, through the 2 points that we want to add. And what we would do in this case, if we want to add 2 pairs of points, is that we draw a cubic polynomial through these 4 points. So this is uniquely defined. It will intersect the curve in 2 more points. Then there's again some reflection, and we get the sum of these points. So there's some nicely geometric way of how to see that this also has a group law in it. Okay, but so now we know a bit how these objects look like that we have in dimension 2. And the question remains, what about isogenies in dimension 2? So as a reminder, before we talked about n isogenies in dimension 1. So those were just isogenies that had as kernel a cyclic group of order n. Now in the 2-dimensional setting, we look at maps that have as kernel the product of 2 cyclic groups of order n. And here, yeah, I didn't draw these similar picture as on the other side, but this is, so one example is that we have such an isogeny between 2 Jacobians of hyperelliptic curves. What makes the situation here already a bit more difficult is that, well, there are different options. We've seen that there are 2 different objects that we have in dimension 2. And what this means is that for these kind of isogenies, we actually have 4 different kinds of maps. So we have the generic ones that just go between the Jacobians. And then we also have something called a splitting map, which means that we go from a Jacobian to a product of elliptic curves, or somehow the dual one, that we go from a product to a Jacobian, which is called gluing. And then we also have diagonal maps or product maps. Okay, so so now we have the objects in dimension 2 and also the isogenies. This means, similar to before, we can also look at isogeny graphs. The vertices of this graph are, on the one hand, products of elliptic curves. So in this graph, I've drawn them in blue. And we have edges between those products. Most of these edges just come directly from the 1-dimensional setting, because we have isogenies between the individual elliptic curves. And so we can also get isogenies between the products of elliptic curves from these maps in the 1-dimensional graph. Apart from those blue vertices, we also have green vertices, which stands for the Jacobians of hyperelliptic curves. And those green vertices are actually much more than the blue ones. And now there are also many more edges between these green vertices than between the blue ones themselves. And then finally, we also have those 2 other types of vertices, which go from the green vertices to blue vertices, or the other way around. I should say that, so on the previous slides where I showed you those 1-dimensional isogeny graphs, those were actual isogeny graphs. Here I got a bit lazy, and this is not an actual isogeny graph. What is correct is, if you look at this prime 53 and the super special vertices in this case, or super special abelian varieties, then the number of green vertices and the number of blue vertices should be correct. But the edges only resemble more or less how many we have of each of them, but they are not actual isogenies. But it should at least illustrate some of the important properties of this graph. And just to summarize them, so one thing that will become very important is that the green edges are really a lot more than the blue edges. And it is even so, given some green vertex, it's supposed to be hard to find a path to a blue vertex. This could be a bit misleading in this picture here, but this should be a hard problem. And apart from this, we also, of course, have the property that we can define a one-way function in this graph, which is given by, again, fixing a starting vertex, then taking like a path in the graph and only outputting the end vertex. And so having seen those analogies, you might wonder, okay, can we also just generalize all the isogeny-based primitives that we have in the 1-dimensional setting to dimension 2? And well, people have asked these questions before. And the first suggestion was to generalize the CGL hash function to dimension 2. And then yeah, it turned out later that there were some subtleties in the two-dimensional graph. You cannot really see this on the previous slide, but there are some very easy collisions that you can get if you just allow all paths in the graph. And so this hash function, the first proposal, was not secure, but it could be fixed by just essentially not allowing all the different paths that one can take and restricting this to some special paths, so to avoid easy collisions in the graph. But this is something that works, and maybe surprisingly to many people, this is even faster than in dimension 1. Or I would say maybe, generically it's about the same speed, but what happens is that in dimension 2, the isogeny graph is much larger than in dimension 1. And so to obtain the same level of security, one can reduce the size of the prime field that we are working with. And so that the computations are essentially the same in this setting still. And so the running time will be better in dimension 2 than in dimension 1. In between those two papers, there was another paper suggesting to generalize the SIDH key exchange to dimension 2. This was first proposed by Jan Botti and Victor Flynn, who also instantiated this. In this case, it's a bit different to the CGL hash function. There, it's actually much slower to instantiate in dimension 2 than in dimension 3. And I think the initial version of the key exchange took around a minute or something like this. So it's not very, so it wasn't considered that much. And later we also worked on an improvement because so in the first proposal, it was still missing a method for selecting secret keys at random. And this is something that we added later. Okay. So that's now the isolated dimension 2 research. Okay. And what I also wanted to say, so you see, I only looked at, said something about the protocols on the left-hand side with this chaotic isogeny graph, and actually a generalization of the other protocols about group actions is still an open problem. But now we come to some exciting research where dimension 2 meets dimension 1. And maybe if you might all have heard about this already, but what I want to tell about is Krani's lemma. This lemma didn't only appear in 2022, but it kind of got popular in the isogeny-based community in 2022. And what it says is that there is a relation between one-dimensional isogenies and two-dimensional isogenies. And this relation is given by relating isogeny diamonds in dimension 1 to product isogenies in dimension 2. So what's an isogeny diamond? An isogeny diamond is just a configuration of isogenies which commutes. This is similar to like the square that we've seen before in the Diffie-Hellman protocol. And if we have such an isogeny diamond in dimension 1, then this induces a product isogeny in dimension 2 between two products of elliptic curves. And what's very important is that we can compute this isogeny, this product isogeny in dimension 2 directly if we are given some interpolation data on the isogenies in dimension 1. And here with interpolation data, I mean the images of points from the first two isogenies on their codomains. Why is this relevant for cryptography? This is because it can be used to attack the cryptographic one-way function if, in addition to the two end vertices, or the starting vertex and the end vertex, we are also given this additional interpolation data. So to say a bit more, so what we are given is two elliptic curves, E and EA, and interpolation data, so points P and Q on the starting vertex, and the images of these 2 points, FA of P and FA of Q, under the isogeny FA. So here I'm using the same notation as in the previous slide. And this is essentially the hardness assumption underlying the SIDH protocol. And now the idea from the attacks on SIDH by Kastrik de Cru and Maino Martin del Pani Pope Wesolowski, and also in the end by Robert, is as follows. So we want to apply Carney's lemma. So the idea is that we construct an isogeny FB that starts to obtain an isogeny diamond. Then we use Carney's lemma to obtain the product isogeny F, which now, because we have this interpolation data, Fa of P, Fa of Q, and we can also compute this interpolation data along the isogeny Fb, because this is the isogeny that we chose ourselves. So we can directly compute this product isogeny F. And then we can use this product isogeny F to actually evaluate the small isogeny Fa that we didn't know on arbitrary points. And this allows us to recover the isogeny Fa. This description of the attack simplifies many things. For instance, the way that I describe the degrees that we are having, and it's not always easy. So, I mean, in the protocol, we know the degree of Fa, and we need to construct an isogeny Fb so that that the degrees add up to the degree for which we are given the interpolation data. And in general, if this is like a large prime or something, it's not easy to come up with an isogeny of this degree and compute it efficiently. But there are some tricks of how this can be done, especially if this vertex E that one starts with is a special vertex with a known endomorphism ring. But this is also the reason, something that I will come back to later, that the original version of the attack is only heuristically polynomial time. We've seen that it's actually super fast, but at least for the SIDH instances, but at first there was still some hope that maybe one can still find a secure variant of SIDH where the attack doesn't apply. Okay, one slide on some computational aspects of the attack, just because this is my main research area. And so what we, in the protocol in the end, what we will have is we have interpolation data on 2 to the n or 3 to the m torsion points. This means that for the attack to work, we need to be able to compute either 2-2 isogenies or 3-3 isogenies. Interestingly, those are the same type of isogenies that had to be used in the generalization of the SIDH attack to dimension 2, which was done by Flynn and T. Okay, so how can this be done? For 2-2 isogenies, in the original implementation of the attack, this had been done using the so-called Richelieu correspondence. Yeah, a few words about this. This is, these were not explicit formulas, but it still required some computations, and especially a small Gröbner basis computation to evaluate these maps. And shortly after, there appeared some papers of how to do those kind of computations, also just using explicit formulas, and either in Mumford or Kammer coordinates. So the Mumford coordinates are a bit like the ones that I told you about before, that we can just think of elements of the Jacobian as pairs of points. And then the most recent result uses theta coordinates, which I think we will see later a little bit. And this is actually these are the currently fastest formulas to compute such isogeny chains. So these 2-2 isogenies were needed to attack Bob's secret key. If we want to do the same for Alice's secret key, we need 3-3 isogenies. This has to do with the fact that the SIDH protocol is not completely symmetric. And the original attacks actually didn't come with an implementation for this case. I mean, from a cryptanalysis side, this is absolutely valid. If you can attack, if you can recover Bob's secret key, the protocol is broken. But we still wanted to see if we can also make this work for the other side. And the main issue why this wasn't implemented before is that already going from 2-2 to 3-3 isogenies, things become a lot more complicated in a two-dimensional setting. That's also the reason that the CGL hash function was quite fast, because this only used 2-2 isogenies. And the SIDH protocol, the generalization of this to dimension 2 was quite slow because it needs both 2,2 and 3,3 isogenies. Okay, but we obtained an implementation of this, and now this year there also appeared a new paper also finding the explicit formulas in terms of these new theta coordinates. One thing maybe you might wonder is why I mean, the SIDH protocol is broken. Why do people still want to make the attack faster? The real reason is not that we want to make the attack faster, but as you will see soon, the attack also resulted in some new research using the attack in for constructive purposes. Okay, and so for this, to see these new purposes, we actually want to go to higher dimensions even. So what does it mean to go to higher dimensions? I've already shown you the pictures before. So in dimension 1, everything we had were elliptic curves. In dimension 2, we had these two different kinds of objects, products of elliptic curves and Jacobians of genus 2 curves. Now, the next question is, what happens in dimension 3? Maybe you can already guess what the first picture will be. It's based on the observation that 1 + 1 + 1 is 3. So what we do is we just take the product of 3 different elliptic curves. This gives us something of dimension 3. And in a similar way, we also have that 1 + 2 is 3. So we can also take the product of an elliptic curve with a Jacobian of a genus 2 curve. This will also produce something of dimension 3. Again, those are not really the generic objects, but more the ones that appear, not so often. And for the generic ones, what we do is we look at Jacobians of genus 3 curve. And now, depending on how you view this, there are also 2 different types of such Jacobians. The generic ones are the ones that you see on the right. So this is the Jacobian of a plane quartic. So just a plane quartic is just a curve defined by an equation of degree 4 in the plane. And the case that appears less often is that we have the Jacobian of a hyperelliptic curve. So this is again a curve with an equation y² = f of x. But now the polynomial f has some higher degree. So before we had degree 5 and 6, so now we will have degree 7 and 8 as possibilities. Okay, why do I think that those higher dimensions are actually relevant for cryptography? The attack already only needed dimension 2. And the first reason is that it's relevant for cryptanalysis. What I mentioned before was that the original version of the attack was only heuristic, and a full version with unconditional polynomial time attack on the SIDH protocol, even with unknown endomorphism rings, was then shortly after publishing the attack found by Robert. And this actually required working in dimension 8. And so we cannot even stop at dimension 3, but we really need to understand all the high, or at least many higher dimensions in isogenies. And what's very nice about the attacks is they also served as a new tool. And one of the most important new tools are the so-called HD representations. What this means is that for an isogeny that we have in dimension 1, so an isogeny between elliptic curves, we can always find a higher dimensional representation, which can be evaluated efficiently. And this means even if we have a prime degree isogeny in dimension 1, where the evaluation usually would take O of n times, so O of n degree, we can find a nice representation in higher dimension of this, for which we can evaluate it in time logarithmic in the degree. So even for mathematical purposes, this gives us a very nice tool. And it also has been used in some recent paper for creating new number theoretical algorithms. But it also has a lot of applications in cryptography. And for instance, there are just after the attack, so not even in the range of 2 years, many new protocols appeared that make use of this HD representation. I hope I didn't forget any of the new protocols. Maybe I think the most popular one that was also presented at Eurocrypt this year is dSign HD. Probably you've heard about the SkiSign protocol, which is submitted to the NIST competition. And this SkiSign protocol has many nice properties, but one problem with it was that the signing took quite long of such in the signature scheme. And an idea here now is to sign with a one-dimensional isogeny and use this to construct this necessary interpolation data, and then use the HD representation to also verify this efficiently. And so I think this is a very new, exciting scheme that will make SkiSign a lot better. And maybe also, so very recently, there were 3 new papers that appeared. And so in the original proposal, the SkiSign HD, it was necessary to compute in dimension 4. And with the SkiSign 2D proposals, it's actually now even possible to do all of this in dimension 2. Okay, so maybe just some things of what we can do at the moment. So I said that we need to go to even higher dimensions. What do we know there? So somehow these pictures that I showed on the left, maybe 2 slides ago, of how you can think of those higher dimensional objects start to work in dimension 4. Not only because I don't know how to draw something 4-dimensional, but another problem is also that we cannot even represent every abelian variety in dimension 4 as a Jacobian of something. So there, the situation gets a lot more difficult. However, what we do know is we have such nice representation that's given by theta coordinates that we can always somehow embed our abelian variety in some space of dimension 2 to the g, where 2 to the g minus 1, where g is the dimension. So this means, like in dimension 1 for elliptic curves, we can embed this in dimension 1 for the surfaces. We need dimension 3 and so on. So this doesn't blow up too badly. What about isogeny computations in higher dimensions? Here it really depends a bit on the dimensions. So in general, there exist algorithms to compute such isogenies. For instance, Damien Robert also described a general algorithm for computing L isogenies, where L is equal to 2. And this has been optimized in the cases where the dimension is 2 or 4. And for the other dimensions, as far as I know, there don't really exist implementations at the moment. And for the case that L is not 2, the situation gets considerably more difficult. However, there exist algorithms to compute such isogenies. It's only that in the past, they've mostly been used for mathematical research. And so they are not optimized for applications in cryptography. So from a computational perspective, there remains a lot to be done to make those, or to improve those higher dimensional new protocols. Okay, and this already brings me to the end. So what I want to say, and I hope I could convince you a bit, is that this is an exciting time at the moment for isogeny-based cryptography. And in particular, if you like this higher dimensional setting. And at the moment, there also remain many things to be done. For instance, we still need to optimize those higher dimensional isogeny computations and see how far we can get, and also up until which dimension this is actually practical, what we to be used in cryptography. Apart from this, I mean, we've seen that there are so many new protocols that just appeared in the last 2 years. And I think that there is even more potential to use those HD representation, maybe also to create some fancy cryptography. And finally, something that I think isn't really done so far is to really exploit the full structure of the isogeny graph. Because what happens at the moment is when we use those higher dimensional isogenies is that we always use isogenies that somehow come from isogenies in dimension 1. But what we actually have is that those isogeny graphs in higher dimension, they are much larger than in dimension 1. And so there's much more structure that could be used to create new protocols. And I hope that we can also find some constructive applications for this large structure of the graphs. And on the other hand, I think it's super important to study those graphs also for cryptanalytic purposes. So we've already seen that it's from the SIDH attacks. I think they convinced us that it's important to understand this higher dimensional setting and also to analyze the new protocols. Of course, it's even more important to do so. Okay, so that's all I wanted to say. Thanks for your attention.
Thank you very much. So we have plenty of time for questions, so I'll run around. We have a hand up.
Thank you for the talk. Is there a possibility that all the curves you introduced in this talk cannot be represented in the polynomial representation?
I'm not sure what you mean by the polynomial representation.
I mean, there is a possibility. There can be a possibility that the coefficient cannot be represented in the polynomial.
You mean efficient representation?
So you mean here?
Yeah.
So I mean, it's known that so about the running time is that if you compute such an LLLL isogeny, so we're here. So I mean, if I say multiple L's, it means that we have a product of cyclic groups of order L G times. And then it's known that there exists algorithms that are polynomial, so in O of L to the G. So linear in the size of the kernel of the isogeny.
Thank you.
I see a hand up over there. If you don't mind, we are streaming out, so you have to get everything on mic. All right, so over there.
Hey, thanks for the nice talk. I had a question about like slide 17, you had all these constructions. I was wondering what's the high level hard problem that they rely on. I think maybe it's a bit different, but for instance, ski-sign HD.
And that's a good question, yeah. So what's maybe, yeah, to say this first, what's actually nice about ski-sign and ski-sign HD, so in ski-sign, the underlying hard problem was an ad hoc problem, more or less. That, I mean, in general, also relied on finding an isogeny between two elliptic curves, but there were also some ad hoc assumptions about like how random the isogenies are that are constructed there. And now with the ski-sign HD version, the underlying security assumption is much more natural. So it's really that we cannot find an isogeny between two elliptic curves in the one-dimensional setting.
So now I was just wondering, like, maybe it's a stupid question, but I assume that these schemes they don't use torsion points. They're also not using the seaside formalism. But then why are similar schemes not possible for the dimension 1 base? Like why is dimension 2 or higher needed here?
So they also use torsion point information, and actually what I think all schemes have in common that at some point they compute an isogeny in dimension 1, and then they use this HD representation to represent it in dimension 2. And this HD representation can then be somehow used as a trapdoor. So for example, in the ski-sign example, you sign in dimension 1, and then somebody else can verify in dimension 2 that you actually know the underlying isogeny. However, you have to take care that you don't give an attacker enough information to actually recover the isogeny in the beginning. And so there you have to mask the torsion points that you actually send around. And does this answer your question? Or?
Yeah, I'm just wondering why the torsion pointed text then don't lie.
So, I mean, what we don't do here is a key exchange protocol. So it's still not possible, I think, to have a key exchange as before from this, but you somehow can introduce a trapdoor by using those HD representations.
Right, I'll come back to you later. So this.
Yeah, so thank you for a very nice talk for dummies in isogenies. And like, so then also a dummy question. So why elliptic curves? So why is there like not something else that we can also maybe consider? Like, so what is a so nice property of these objects that are like why they're so the best possible candidates to consider for this type of like, so if we can take some other type of curves, maybe we can do similar techniques, put them in the higher dimensions, so why not? Or if there is something else.
So yeah, what makes elliptic curves special among all curves that we have in general is that there's a group structure. And really elliptic curves are the only curves that have such a group structure. And so it's only the only type of curves for which we can define isogenies. So in general, so in a more mathematical sense, usually if you define an isogeny, you define it as a map between abelian varieties in general. And then the elliptic curves are just a one-dimensional case of this. And so, yeah, I think for other curves, we can't really do anything similar like this.
Second.
Thank you. Yeah, I enjoyed the talk. And I particularly enjoyed your explanation at the end that we're sort of throwing away the high dimensional structure with the current crypto applications. So I just wondered what your feeling is for what types of applications could be opened up by looking at designs that use this richer structure in the higher dimensions.
So one thing, for instance, is, okay, I have to go back quite a lot. It's here. All this right-hand side, which is still an open problem. So I think it would be super interesting to see if we can make this somehow work in the higher dimensional graph. And if we can find a good generalization of this, then I would expect that we can use prime fields of a much smaller size to achieve a similar security. And depending on how good we can make these isogeny computations in higher dimensions, this might then be faster than in dimension 1. However, I also know that there are many people who have already tried to work out such a generalization, for instance, of the seaside protocol to dimension 2. And I think so far this hasn't been successful. On the other hand, we've also, so this was before the break of SIDH and before these higher dimensions got so much attention and there was so much work in optimizing the protocol. So I could imagine that this will maybe also somebody else will start to tackle this again, this problem, and make it work.
What about like fancy cryptography?
Okay, yeah. So the question was, what about fancy cryptography? And there, yeah, I have to say, I mean, I'm a mathematician, so I'm not, yeah, it's not my real area of expertise to think about fancy cryptography. But I think that this trapdoor that we have in the HD representations could be something that can be used for fancier cryptography. Yeah, I already talked a bit with my colleague Doreen from Bochum because she is an expert in the protocol community about what kind of protocols we could imagine, like, for instance, blind signatures or also PEG protocols or something like this. But I mean, we don't have any concrete proposals yet for this one.
Hi, thanks for a lovely talk. I also have a question about using this high dimensional structure. So I think maybe as your penultimate slide, you had a summary of all the known implementations that we have for different dimensions and yeah.
This one?
No, one more? For the actual computing of these, yeah, exactly. So what do you think are the barriers to actually using these isogenies, which are not just representations of one-dimensional isogenies? Is it just that the implementations don't yet exist, or?
Yeah, so one thing is that the implementations are not not optimized for cryptography yet, and also that there are still some open problems in the theory behind those graphs that we don't know how to solve yet. And something else is also, so I said in the beginning that those representations that we have by theta coordinates are very convenient. However, what you see is that so the dimension of an abelian variety is G, and you see that this dimension of the space, so which is the number of coordinates that we need, is 2 to the G. So it grows exponentially. This means I wouldn't expect that, I don't know when it stops being practical in the end, but necessarily if the number of coordinates grows exponentially, this is also the same for the computations in the end. So.
Thank you.
All right, we have a hand up over there. My job.
Hi, thank you very much for the super nice talk. I had a question about this left-hand side, right-hand side distinction that you had. So for the seaside schemes, is there a sort of a deep or a deep reason for why people can't generalize this to higher dimensions, or do you expect people to just manage in a year or two?
So maybe what makes the left-hand side easier is that there, okay, that's not super visible on those graphs here, but on the left-hand side, we only always consider 2 colors. And somehow, since there are so many edges, even of those 2 colors, and they are kind of chaotic, it's enough we still have enough paths in the graph. And so to make it more precise, on this side, we consider all the supersingular elliptic curves. And on the other side, on the right-hand side, we only consider the supersingular elliptic curves that are defined over FP. And there are less of them, and in particular, there are also less edges. So you see that for each color, there's only one incoming and one outgoing edge. And so we really need many more colors to make paths in the graph that then cannot be found afterwards. And so, I mean, this is a baby example there. I could only include 3 colors, but in general, so I think for the first seaside proposal, there are like 70 colors or something like this. So this means in higher dimension, we would really also need to compute those LL isogenies for 72 different primes. And it's already super difficult to do this for L equals 3. And I haven't seen any like efficient implementation for L equals 5 even. So from a computational perspective, this side is already much more difficult. And then also from a theoretical perspective, it's, at least to me, not super clear what the correct generalization would be. So here we have this nice group action, which comes from the endomorphism ring of the elliptic curve. And in higher dimensions, the endomorphism ring also becomes more difficult. So yeah. I'm even not completely sure what the correct way is to generalize this.
Thanks a lot. That was super clear.
All right, so if there's no further questions, I think we can thank the speaker and break for lunch.